So let's talk about the other part of pharmaceutical organic chemistry. The first question that you have here is, using a well-labeled diagram, illustrate the different class of hybridization found in organic chemistry. Now, the first thing that we need to take cognizance of is the types of hybridization. We have three types of hybridization in organic chemistry. The three types of hybridizations are Sp3 hybridization, Sp2 hybridization, and Sp hybridization. Now, these three types of hybridization have different things they signify or different ways to identify them. Now, let us take the first one, which is Sp3 hybridization, and analyze it together. Now, Sp3 hybridization is that type of hybridization whereby all the electrons present in the valence shell are what? Hybridized. Now, first of all, let us write the electronic configuration of carbon, as carbon and hydrogen, especially carbon, is the backbone of all organic compounds. So let us write out the configuration of carbon. In the periodic table, carbon has 6 electrons, but it's a group 4 element. Now, writing the electronic configuration for carbon, you have 1s what? 2, 2s2, and what? 2p2. This p orbital has 3 degenerate orbitals, which are 1x. If I say this is 1s2, 2s2, the p orbital has 2px, 2py, and 2pz. Now, these 2 electrons, we are going to fill 1 each into these orbitals. So this will be 1, and this will be what? Another 1. Now, it means that one of the p orbitals is what? Empty. Is that not so? In most cases, it is often represented with a box like this, where you have 1, 2, 3. If this is 2px, 2py, and 2pz. According to Hund's rule, it's proper that you fill singly before pairing. So we fill 1 electron in 1, and this is what? 2. It means that we have an empty p orbital. Now, this x orbital has just 1 orbital in it, which is 1x. This other 2s orbital also has just 1 orbital in it, which is what? 2x. Now, this 1s orbital has its complete 2 electrons. This 2s orbital also has its complete 2 electrons. Reason being that the x orbital can take a maximum of 2 electrons. The p orbital can take a maximum of 6 electrons, which are shared into 2 each into each of the degenerate orbital, 2ps, 2py, and 2pz. And then the d orbital can accommodate a maximum of 10 electrons. The f can take a maximum of 14 electrons. Now, having understood this, let's now come back to what we were doing before. Now, we discover that since the p orbital can accommodate a maximum of 6 electrons, and we have 2 electrons here, and of course, according to Hund's rule, it states that while filling electrons into appropriate orbitals, electrons are filled singly before pairing. So we have to fill the 2 electrons singly before we pair. Now, in this state of carbon, it is called the ground state. The ground state configuration. But when carbon is excited, maybe due to some factors that may act on it, what will happen? One of these 2x electrons will be promoted. Now note that if you have the configuration 1s2, 2s2, and 2p2, you agree with me that these 2s and the 2p are the valence shell. These s and p are just orbital. So when they ask you about the valence shell of carbon, you say it has 2x and what? 2p electrons, which is 2 and 2. Is that understood? So in any case, if they give you the electronic configuration of any compound, this coefficient here, the highest, is always the valence shell. If there are two of them, you add the two electrons together to get the number of valence electrons. So in this case, you have 2s and 2p. So if they add 2s plus 2p electrons, how many electrons are here? 2 plus 2, this will give us what? 4 electrons. So that is how to identify the valence electron. First of all, identify the valence shell. The shell with the highest coefficient here, which is 2 here, and what? Also 2 here. Now, had it been you had, let's say, 1s2, 2s2, 2p, let's say 3, and then let's say 2p6 here, and then 3s2. If you are given anything like this, which of these ones here have the highest coefficient is 3? And how many of those 3 are there? Just 1. So the valence shell here is what? 3. And the number of electrons here will be what? 2. How about if you have 1s2, 2s2, 2p6, 3s2, and 3p6? Now you agree with me that the valence orbital here is 3s2, and valence shell rather is 3s2 and 3p6, which will give us a total of how many electrons in the valence shell? 2 plus 6 is how many? 8 electrons. Now, this is just by the way. I was trying to revise something for you to understand better. So the valence shell of carbon has how many electrons now from what we've said? It has 4 electrons. Because this 2s is a valence shell and 2p also is a valence shell. 2s have 2 complete electrons and 2p has 2 electrons out of its 6. Now, whenever carbon is excited, one of the electrons on the 2s orbital will be promoted to what? To the 2p orbital. And then 2pz will now be filled up with 1 electron, or halfly filled rather, with 1 electron. Because when we say it's filled up, that means all of them are what? Paired, like the complete 6 electrons are present. So, at this state, carbon can what? Hybridized. Now, in sp3 hybridization, 1x orbital, which is from this 2x. Now, you should take note of something, that in hybridization, it is only the outer orbital or outer shell that does what? That goes into the hybridization. It's only the outer shell that goes into the hybridization. This is not an outer shell. I've explained what an outer shell is. Now, if we write the outer shell configuration for carbon, you are going to agree with me that we'll have something like this. This will be the outer shell configuration of carbon. You are going to have something like this. The outer shell starts from 2p. Let's say the full electronic configuration to distinguish is you have 1s2, then you now have 2s2, 2s, according to the one I just gave now, the degenerate here will now be 2s1 because one electron was promoted, and the other one will be what? 2p3. This 2p3 is splitted into 2ps1, 2py1, and what? 2pz1. Now, in this case, in sp3 hybridization, what happens is the atomic orbitals of 2s and 2p, all of them hybridizes to form 4 equivalent molecular orbitals. They hybridize to form how many equivalent? 4 equivalent molecular orbitals. Now, in that case, we can say that hybridization is the missing of atomic orbitals to form molecular orbitals. Missing of atomic orbitals to form what? Molecular orbitals is what hybridization is all about. Now, in hybridization, the number of atomic orbitals that miss must be equal to the number of molecular orbitals that will be formed. So in this case, if we have, like I said, that is only the outer electrons that hybridized, or the outer shell. So we have 1, 2, 3, 4. That means 4 atomic orbitals. So if the 4 atomic orbitals hybridize, what are we expected to have? We expected to have what? 4 molecular orbitals. Is that understood? So if we take the first one, now let's remove the 2's and whatever that we have. Let's put it as S, P, X, Py, and Pz. Let's remove the 2 as the valence or the outer shell, and let's remove the electrons. So what are we going to have? We are going to have something like this. If we remove the 2, we are going to have S, we are going to have P, P, P. One of the P is S, another one is Y, and the last one is what? Z. So in this case, one S hybridizes with the 3P, which is this S, P, 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 to give us what? Sp3. Because we said Sp3, all of them what? Hybridized. Now, this P, now we are done with this S. If this P hybridized with this S, this P, and this P, it will also give us what? Sp3. Because this P is 1 plus 2 plus 3 plus this S, Sp3. Now, same way goes to this one. This one will also form what? Sp3. Because this P, 1, 2, 3 plus this S, Sp3. Including this one will also form what? Sp3. So you see that the number of atomic orbitals that hybridized will give the number of molecular orbitals that will be formed. Now, how do we use the energy diagram to illustrate this? We are going to draw something now. How do we use the energy diagram to illustrate this? Now, the s orbital is less in energy than the p orbitals. In most cases, is lower in energy than the p what? Orbital. So what we are going to do is, you write x for this. Now you have to indicate the s you are actually hybridizing, because there are 2 s there. So you write 1x. Now on top of this 1s, you can put something like this and then put the electrons. Then you are now going to write 2px on top of this 2ps. Now we said 2ps is what? A little bit higher than what? 1s. So you say this 2ps. How many electrons? If we want to write the electronic configuration, we say is what? 2s1, 2ps1, 2py1, and what? 2pz1. So you now say this is this. Then also it continues 2py. Then you use this to show to you that there are 1 electron. This 2s has 1, 2ps has 1, 2py has 1. Then it continues. This one also has 1, which is what? 2pz. Then you are now going to put hybridization here. Hybridization. Now, the ones that are formed are usually the molecular orbital form. They usually have a lower energy than the what? Than the atomic orbitals that react. So you are going to come here and put this one under a little to show the energy difference. Now, when this hybridized the other time, what did I say? It formed sp3. How many sp3? About 4 of them, because 4 molecular orbitals actually hybridized. So sp3. And then we are going to, you put this here and you put sp3. Put another one and you put what? sp3. Put another one, I put what? sp3. And finally, put another one, I put what? sp3. So this is the energy diagram you are to write. Now, here you are to say these are atomic orbitals. Atomic orbitals. Or you can label it unhybridized atomic orbitals. Are we getting it? Unhybridized atomic orbitals. Make sure you put this hybridization. Then here, you come here and put what? Hybridized. Are you getting it now? What will now be? Hybridized what? Molecular orbitals. Is that okay? So that is for sp3. Now let us come to sp2. As the name implies, sp2 means that 1s hybridizes with how many p? 2p. So we have here 2x, 2px, 2py, and 2pz. Now this one is having one electron, normally before, one electron, and here is what? One electron. Now in sp2, 3 of the orbitals hybridized, leaving one of the p orbital on what? Hybridized. Are you hearing it? 3 of the orbitals hybridized, leaving one of the p orbitals what? Unhybridized. Now, according to what I said before, that the number of molecular orbitals formed is proportional to the number of atomic orbitals that hybridizes. So if 3 atomic orbitals hybridized, it means that how many molecular orbitals will be formed? 3 also. In such a way that this S, let's write it out without the 2. So we have sp p hybridized. So this S hybridized with this P and this other P form sp2. This P with this S and this P form another word sp2. This P with this P and this S form another word sp2. Do we have any other one to react? No. So when 3 atomic orbitals hybridized, it forms 3 molecular orbitals. And one unhybridized, you saw this one here is what? Unhybridized p orbital. Is that okay? Unhybridized p orbital. Now we are now coming to our energy diagram now to illustrate how it is. You will now come here and draw and write it. So this will be what? Sp, or let's say this 2x. The 2s orbital has how many electrons? 1. Now after 2x, what do we have? 2px. This one has 1 electron. After this one, 2py, 1 electron. After this one, 2pz, what do we have? 1 electrons. Now you see that this ps, py, and pz, this, and this, I represented them on the same level, on the same platform. This is because these orbitals are degenerate orbitals. They are what? Degenerate orbitals. What are degenerate orbitals? They are orbitals that have the same energy but different orientation. These 2 orbitals have the same energy, 3 orbitals rather, but different orientation. This one is orienting to the x direction, this one is to the y, and this is to the z. Now, if we want to illustrate sp2 now using the energy diagram, what will it not be? You will now say this is equal to hybridized. Please, these are the label. You should put them. And this is what? Unhybridized atomic orbitals. All these ones, they are not what? Hybridized. You can just put atomic orbitals, or you can indicate it by saying unhybridized atomic orbitals. Okay? Now, according to what I said for sp2, how many molecular orbitals will be formed? 3. And 1 unhybridized p orbital. So you are going to form 3 molecular orbitals, which are what? sp2. Why? Because we have spp normally as the electronic configuration. So if these 3 hybridized, s and 2p, sp2, this p and this s, sp2, this p and s, sp2. So it forms sp2. Okay, you have to bring the energy level lower because this one is. So you say these are sp2, and then you put 1 bond here. Here's what? Another sp2. Then you put this. This one is what? Another sp2, and then you put this. And then you now put this on top a little. Another word? p orbital. This p orbital here, you put 1. Now this one is telling you that the energy here of this unhybridized is higher than the energy of the hybridized molecular orbitals. Now this leads to the formation of what? A pi bond. That is why in some compound you see double bonds present in them. So this is hybridized molecular orbitals. Hybridized what? Molecular orbitals. Hybridized molecular orbitals. How about this p orbital? If I want to bring it down here, what do you call this? Now you should label it under it, but because there's no space, that's why I'm bringing it down. This is unhybridized what? P orbital. Unhybridized p what orbital. These are the labeling. Each of these will earn you your mark. This is supposed to be hybridization, okay, not just hybridize. Hybridization, okay. So let's take note of this. Now, with this understanding, I believe we should be able to do the one for sp, right? Sp will just be how many orbitals will hybridize? Just 2. So if we have sp, p, p, for sp, only 2 orbitals will hybridize. And according to the rule, when 2 orbitals hybridize, you have sp, then this sp hybridize with this sp, and this p hybridize with this to form another word, sp. So 2 atomic orbitals hybridize to form what? 2 molecular orbitals. And 2 what? These 2 now, they are what? Unhybridized. They will form what? Double bond, double bond. That is why sp hybridization is usually formed in molecule with at least triple bond. So we are also coming here with the same information now that we already know. So you come here and say this is 2x with how many electrons? 1. This is what? 2px with 1 electron, 2py with 1 electron, and then what? 2pz with 1 electron. And then you root this. You say this is what? Hybridization. You must indicate this. And then after this, the next thing that you now have is what? Is the p orbitals. I mean the hybridized orbitals. Now we say for sp hybridization, only 2 did what? Hybridize to form sp2. I mean sp. Let me bring it out. We have sp-pp. Only these 2 hybridize. I will say the number of atomic orbitals that hybridize will give the number of molecular orbitals, right? So if 2 atomic orbitals hybridize, it means we form how many molecular orbitals? 2 molecular, which are what? Sp. This s hybridize with p, sp. P hybridize with s is also what? Sp. Then we are left with what? P and what? P. So we come here and say this will be sp. You put 1 electron there. Then another what? Sp. Another electron. Then you now come here and put, now the energy of this should be higher than that. This is what? P. You put 1 electron here, and what? P. You put another electron here. Are you getting it now? In some cases, you may want to indicate the year. You can say this is pz that did not hybridize. In case you come here, you can say this is what? Py and what? Pz that did not hybridize. So in this case now, what do you form, or what are you likely to form? You form 2 hybridized molecular orbital. That's how you label this. Are you getting it now? Hybridized molecular orbitals, and this is what? Unhybridized. Now, in most cases, you don't know if it is the ps or the py that did not hybridize. Unhybridized molecular orbitals. So you see how it is. Now, while you are drawing, please be careful enough. Don't come and draw like me. Be careful enough to put this thing, this sp. Be careful enough to bring it down to show that to show that the molecular orbital form have a lower energy than the what? Atomic orbitals. And these unhybridized have the same energy with the atomic orbitals. So these ones here are the what? Unhybridized atomic what? These atomic orbitals. These are the atomic orbitals. Are you getting it now? Before hybridization takes place, and so on and so forth. Okay? Now, so that is for hybridization. sp, hybridization, and whatsoever. Is that okay? Now, briefly write on the generation of free radicals. Now, free radicals are generated due to homolytic cleavage of bond, or you can call it homolysis. Homolytic cleavage of bond or homolysis leads to the formation of what? Free radicals. Now, in this process, what actually happens? It happens between 2 compounds or 2 atoms having almost the same polarity or close polarity. For instance, Let us talk about Cl2. Now the bond in Cl2 is like Cl. Now there's a bond between chlorine and this other chlorine atom. If this bond breaks, each of the chlorine atom takes away their electrons in such a way that what will be formed here is what? This and this. These that are formed are called free radicals. So we can say that free radicals are formed from homolytic cleavage of a bond. It can be initiated by sunlight, or we can say it can be initiated by two ways: photolysis and thermolysis. Photolysis is when light is used, while thermolysis is when what? Heat is used to generate free radicals. Is that understood? So free radicals are formed in homolytic cleavage, and it's a type of bond cleavage or bond breaking whereby each of the participating atom after the bond takes their what? Electron, leading to the formation of what? A radical. Is that okay? So that is the generation of free radical. It may be photolysis or thermolysis. Photolysis is when sunlight is used, like this of chlorine is usually by what? Photolysis, UV radiation. You see something like this, then it breaks down to give two free radicals. Why in some cases, like if you have the acid anhydride, I didn't want to come here before, but we just have to. The acid anhydride. Why am I? Let's say you have a molecule like this. Now, if this molecule splits, what do you think can happen? You agree with me that this will break in such a way that each of these will take away their electrons. So we have something like this plus O, and then you have C double bond O and R. Is that understood? So that is homolytic cleavage. That is what homolytic cleavage is all about. A type of bond, or they say right briefly on the generation of free radicals. Free radicals are generated by homolytic cleavage of bonds. It can be induced by sunlight in bracket photolysis or by heat in bracket thermolysis. Homolysis is a type of bond cleavage or bond breaking whereby each of the participating atom takes away their electron after the what? Bond breaking. It is mostly between two atoms that have close polarities, or let's say close electronegativity in such a way that no one is dragging the electron away from the other. Is that understood? So that is for that. Now let's look at the next. Electron availability is vital for chemical reaction. List the factors that affect electron availability and reactivity. Now the factors are: 1, inductive effect. We are not asked to explain, so we list. 2, electromeric effect. 3, we have mesomeric effect. Mesomeric effect. 4, hyperconjugation. 5, steric effect or crowding effect. 6, we have resonance or electron delocalization. So these are the factors that affect electron availability for reactions, or the factor that affect electron availability and what? Reactivity. These are the factors. They are also called electronic effects. Okay? So let's go to the next. In one sentence, define Lewis acid and Lewis base. Now, Lewis acids are electron acceptors. That is what you answer in one sentence. Lewis acids are electron acceptors. Are we getting it? electron acceptors. Why example, say with one example is EG BF3 AlCl3 FeBrO3. All these are what? Lewis acids. Then we have Mg2+. All positive ions, almost all of them are Lewis acid. All electrophiles, they are Lewis acid. So all these are Lewis acid. Now the next one say define Lewis base. Lewis base are electron donor. Lewis bases are electron donor. Now when we talk about electron acceptor, that means there are atoms that can accept electrons. In most cases, we can also say that the Lewis acids are electrophiles, electron loving. Are we getting it? They accept. Because either they have a positive charge, so they need that electron to neutralize it, or they have empty orbital that needs to be filled. For instance, BF3 has empty orbital that needs to be what? Filled. Hence, the reason for why it is what? Called a Lewis acid. Now, Lewis bases are electron donor. Now, for something to be an electron donor, it means that it have what? Excess of electrons for donation. An example of a Lewis base is H2O. H2O has 2 lone pairs of electrons that it can donate. We have Cl-. All these ones, they have what? Electrons that they can donate. Is that not okay? Now, we have, there are so many examples. There are so many. Even ethene, as common as ethene, is a Lewis base. Because of this double bond here, it can donate. So we can also call them nucleophile. Is that understood? But what we answer is just one example each. So you can pick from the plethora of examples that we have here. Now let us go to number 2. The next question. List the various factors that determine the strength of an acid. Now, the factors that determine the strength of an acid are 1. The size of the atom to which the proton is attached. That is 1, the size of the atom to which hydrogen is attached. So as you go down the column in the periodic table, what happens? Atomic size increases. Now, if atomic size increases, what does that mean? It means that as you go down, acidity does what? Increases. So the larger the size of the atom, the higher the what? Acidity. So as you go down the column, because as you go down the column, the size of the atom does what? Increases. As you go down the column, acid strength increases because the size of the atom increases. Now, number 2 is the electronegativity of the atom. Electronegativity of the atom to which hydrogen is attached. Now, the more electronegative the atom is, the more acidic the substance is. The more electronegative the atom is, the more acidic the atom is. Is that okay? Now, the next thing is hybridization. Hybridization. Now, hybridization, the order of hybridization of acidity is in this format. Let's just say list. So you list hybridization. The order of acidity is Sp is greater than what? Sp2 greater than what? Sp3. So a compound that has Sp attached to the hydrogen will be more acidic than what? The other. Is that okay? Now, number 4, we have inductive electron withdrawal. Now, an electron withdrawal group increases acidity. Inductive electron withdrawal. An electron withdrawal group increases acidity, inductive electron withdrawal. What are the electron withdrawal group? For instance, if you put hydrogen and chlorine together, chlorine is more electronegative than what? Hydrogen. Hence, it will tend to what? To withdraw the electrons to chlorine atom, and therefore this bond will be polarized towards chlorine. You're like you are doing this tug of war with somebody, and then the person is more powerful than you. What will happen? The person will drag you to himself. Are you getting it? So you'll be polarized towards the what? The more stronger atom, which is in this case the more electronegative, which is chlorine. So, and then the presence of substituent 2 also affects acidity. The presence of substituent, like if you have, let's say, CH3, CH, then you have F, and then COOH. Now this fluorine here will affect the what? Acidity. Is that okay? Because this electron withdrawing, and the closer this is to this, the more acidic it will become. Fluorine is electron withdrawing, so this present here will do what? Will increase the acidity, and the closer this is to this, the more the effect will be felt by this COOH. So if I give you a compound like, let's say, CH2 and fluorine, and then I gave you CH2COOH, you agree with me that this compound here will be more what? Acidic. Why? Because the fluorine is closer to what? This carboxylic acid than this fluorine. This fluorine is at the back. And the more electronegative the atom here is, the more acidic it is. So even if this atom is here, and let us say I give you CH3, CH, COOH, and then the atom here is chlorine, what would you say? You agree with me that fluorine will be still more acidic than what this, because chlorine is not as electronegative as fluorine atom. So the more electronegative atom have the higher acidity. An electron withdrawing group will what? Increase acidity. Hybridization will also what? Increase acidity. And then the last one is electron delocalization. Electron delocalization. Now, do you know that the alcohol also has some acidic properties in them, but they are not as acidic as the carboxylic acid? Why? Because of what? The electron what? Delocalization present in carboxylic acid as opposed to those present in alcohol. For instance, if you look at ethanol, ethanol is what? Is CH3, CH2OH. Although there is an electron withdrawing group here or whatever you have here, but this is not as acidic as a compound like this. Let's say you have this OH, and then here is arrow, this O. Why? Because of this electron delocalization. You always see electron delocalization will mean resonance. Like this one will come up here to now form C, and then you have O minus, and then you have arrow and what? OH. Now this thing can run until this place also become double bonded. So we can in most cases represent this with dotted line like this going across this like this to show to you that this electron here can be here, and at the same time it can also be what? Here. That process is what is called electron delocalization. It doesn't stay in one place. It has a tendency to be here. That means this electron belonging to this can be here, and in some cases it can also what? Come here, delocalize. Is that understood? So these are the 5 factors that affect the strength of an acid. Now, as a recap to what we said the factors that affect acidity are what? The size of the atom to which hydrogen is attached, the electronegativity of the atom to which hydrogen is attached, hybridization, inductive electron withdrawal, this withdrawal, and then we have electron delocalization. Let's take a look at the next. The next says calculate the pH of the solution if compound Z has pKa values of 6.4 and the concentration of its basic form is equivalent to that of its acidic form. Now, what is the relationship relating pH and pKa? Is the Hadamson-Ezerbach equation, which is pH is equals to pKa plus log A minus all over what? HA, where A minus is the base and HA is the acid. Now, they gave you the pKa value. The pKa value that was given is 6.4. I will ask to calculate for the pH. What will be the pH? Now, in most cases, you may not really need to solve this, but to show that you actually did this, it's expected that you show your workings. Now, whenever the concentration of the basic form is equal to the concentration of the acidic form, the pH is always equal to what? The pKa value. Is that understood? Whenever the concentration of the basic form is equal to the concentration of the acidic form, pH is equal to pKa. So what we are expected to get in this question is pKa is 6.4. It means that our pH will also be what? 6.4. But let us solve to ascertain our answer. Now, pH is pKa. pKa is 6.4 plus log. Now, I say concentration of acidic is equal to that of what? Base. So, our basic form is equal to that of acid. So, we can say that our A minus is equal to what? HA. Are we getting that? Our A minus is equal to HA. It means in place of A minus, we can put HA. In place of HA, we can put A minus and vice versa. Are you getting it now? So, let us put HA here in place of A minus because they are equal. And then HA also here because they are the same. Now, HA cancel HA. What are you going to have here? 0, 1. Now, pH will now be equals to 6.4 plus log 1 is what? 0. So, pH is equals to 6.4 plus 0. And 6.4 plus 0 is what? 6.4. Let us take a look at the next. Calculate the pH of the solution if the concentration of its acidic form. Now, which of them is the acidic? A minus is 100 times the concentration of the basic form. Where's the basic form? Okay, the concentration of the acidic form. Acidic form is HA. Is 100 times the concentration of the basic form. Basic form is A minus. So, what do you think this is going to form now? We say pH is what? pKa plus log A minus all over HA. Now you are given that HA is 100 times what? A minus. So this will be equals to pH is equals to, now if the pKa still remains the same, so it means our pKa is still what? 6.4. And this will become 6.4 plus log A minus is HA is the same thing as 100 bracket A minus. So our A minus still remains. It's HA that changed. So our HA now will be what? 100 bracket A minus. A minus cancel A minus. We are left with 1 here. So at the end of the day, our pH will be 6.4 plus log 1 all over what? 100. Because when this cancel this, it gives us 1. Now pH would be equals to 6.4 plus log 100 is log 1 all over 100 is minus 2. So this becomes pH is equal to minus 2 times plus 1 is what? Is minus 2. And pH is equals to 6.4 minus 2 is what? 4.4. And that is the solution to that question. Now let us look at the next. Calculate the pH of the solution if the concentration of its basic form is 10 times that of its acidic form. Now, the basic form is what? A minus. A minus is what? 10 times that of what? Acidic form. So, A minus is 10 times HA. The pKa is still the same, 6.4. So, what will be the solution to this question now? Our pH, of course, is pKa plus log A minus all over HA. And this will be equals to pH is not known. Our pKa is 6.4 plus log A minus is what? 10 bracket what? HA. Because that's what we have here. We say A minus is 10 times what? HA. All over HA. HA cancels HA. This will give us 1. 10 over 1 is same as 10. So we have pH is 6.4 plus log 10. And of course, if you press log 10, your calculator is going to give us 1. Let's try it. Log 10 will give us 1. Log 10, it gave us 1. So this will be pH is equals to 6.4 plus 1, and that will give us what? 7.4. So that is solution to that question. Now, discuss the following: Sp2 hybridization and heterolytic fission of bond, nucleophile inductive effect, electrophile mesomeric effect. Now, let me discuss Sp2 hybridization of bond. We've discussed Sp2 before now. Now, we said Sp2 hybridization is a type of hybridization whereby three atomic orbitals spp hybridizes to form 3 molecular orbital of energy lower than those of the atomic orbitals that hybridize. Are we getting it? So that kind of hybridization is what? Sp2 hybridization. And I've shown to you how. Now we said if we have spp, for sp2 only the s and 2 p we hybridize to form how many molecular orbital? 3 molecular orbital. And if we want to show this with the energy diagram, we can say this is what? S, 2s with 1 electron, 2p is a little bit higher. So we say this is 2ps. Then we have 2py, and then we have what? 2pz. This 1, this 2, and this 3. And then you say hybridization. It hybridizes. And when it hybridizes, what are you going to form? You form 2s. We form a molecular orbital that is lower. Are you getting it? In energy. So this becomes sp2, and what? sp2, and another unhybridized p orbital. Because when all of them reacted, you have sp, p, p. When these two reacted, there is one that did not react. This last one, z. So you say this is what? 2pz. You can say pz. This one did not react. So you label this one unhybridized p orbital, hybridized molecular orbital, hybridization. Then we say this one are what? Atomic orbitals. You should be able to do this. And you should note this, that the molecular orbitals have energy that are lower than those of the atomic orbitals that hybridize to form this. And another thing that you also need to know is in sp3 hybridization, the S character is 33.33%. And then the P character is what? 66.66%. Now, how do you calculate this? You have sp3, right? sp2 rather, not 3. sp2. Now, how many S are here? 1. If you write the total molecules out, is what? spp. Is that not so? How many S are there? 1. Total number of molecules is what? 3 times 100%. This will give us 33.33%. Now, how many P's are here? 2. So you say 2 over 3 times 100%, and this will give us 66.66%. So this is how to calculate the percentage S character and the percentage P character of this hybridization. All those things are things that you should discuss. Another thing you can now say is that in molecules with sp2 hybridization rather, the bond angle is usually 120 degree. The bond angle is usually what? 120 degree. Their molecules have bond angle of 120 degree and are usually trigonal planar in shape. Usually trigonal planar in shape. Is that okay? So that is that for sp2 hybridization. Now let's go to heterolytic fission. Now in heterolysis, we said homolysis splits to give what? Free radicals. Okay? Now in heterolysis, what happens is it splits to form ionic intermediates instead of free radicals. And of course, you know the reason why they will split to form ionic intermediate, which are what? Cations and what? Anions. Reason being that the electronegativity difference between the two atoms is large. So when they split, they form ionic intermediate, positive charge and what? Negative charge. Now, if the molecule contains a carbon, let's say you have something like the CH3, CH2, then CCl. Let's say CH2Cl. Now, you agree with me that this is a carbon and this is chlorine. If this split, this is partially negative normally before, and so this will form what? Negative charge, and then this other group here, CH3, CH2, CH2 plus, will form a positive charge. And this positive charge that it will form now is what is said to be called a carbocation. So this one will form a carbocation. Now there are some cases like the Grignard reagent, which is CH3MgBr. If this one splits, carbon is more electronegative than magnesium rather. So carbon will carry the negative charge and you now form something like the CH3 minus and what? MgBr positive. This one is what? A carbanion. So the type of bond cleavage that leads to the formation of ionic intermediate is what is called what? Heterolytic fission. It leads to the formation of cations and what? Anions, which are called ionic intermediate. If the cation contains carbon, you call it carbocation. While if it contains positive charge, negative charge, you call it what? Carbanion. So that is for that. Now the next one is nucleophile. Nucleophiles are nucleus-loving species. They are nucleus-loving species. All nucleus-loving species are called nucleophiles. All nucleus-loving species are called what? Nucleophiles. Nucleophiles are nucleus-loving species. They are electron-rich. They are electron-rich. Now, you agree with me that the nucleus, according to the postulate by Ernest Rutherford, that the nucleus is positively what? Charged. So, if they are nucleus-loving species, it means that because the nucleus is positive charged, they are what? Either negatively charged or they have what? Lone pairs of electrons before they can attract a positive charge. So, nucleophiles are nucleus-loving species. They are called nucleophiles. Nucleophiles are nucleus-loving species. What am I writing? Are called nucleophiles. Okay, nucleophiles are nucleus-loving species. They are electron-rich. So any atom that is electron-rich is said to be a what? A nucleophile. And another thing again is that they are either negatively charged, not positive. They are either negatively charged. They are either negatively charged or neutral. They have lone pairs of electrons. They are either negatively charged or have lone pairs of electrons. So those are nucleophiles. And examples of nucleophiles are, you have CH3. All these ones, they are nucleophiles. Okay? All these ones, they are nucleophiles. Let's say something like this. These are nucleophiles. Now you have OH minus. All these are what? They are nucleophiles. Is that okay? All these are nucleophiles. So nucleophiles are either negatively charged or they have lone pair. Another example of a nucleophile again is NH3. NH3 has 2 lone pairs on top here. So these are all nucleophiles. Now the next one is inductive effect. What is inductive effect? Now, inductive effect is a permanent polarization that is formed when a more electronegative atom is attached to a less electronegative atom. Are we getting it? Thereby pulling the electron cloud from the more electronegative, from the less electronegative atom to the more electronegative atom. Now, nucleophiles are the polarization is often indicated with arrows pointing towards the more electronegative atom. Are we getting it now? So in this case, you see the way this compound is. You have CCl. Chlorine is more electronegative, so it becomes partially negative. And then carbon is less electronegative, so it becomes partially positive. Now, this thing you see here, the bond is not like this. The chlorine pulls the atoms to carbon, and then the bond will be moving towards this direction. Now, of course, if the chain continues, you have, let's say, CH2 like this, and then CH3. Inductive effects can be neglected when after the third carbon. That means from here downward, it's no longer what? Effective. So we can say inductive effect is a permanent polarization that occurs when a more electronegative atom is attached to a less electronegative atom, pulling the electron cloud from the less electronegative atom to the more what? Electronegative atom, thereby forming a partial positive and partial negative what? Charge. That is everything about inductive effect. Now we have the plus I inductive effect and what? Minus I. The plus I is for compounds like this, while the minus I is for the more electronegative what? Atom. This one undergoes plus I, while this one what? Undergoes minus I effect. So that is for inductive effect. The next one is electrophile. As the name implies, electrophiles are electron-loving species. Electrophiles are electron-loving species. Now, why do you think they are electron-loving? Because they don't have electron. They are electron deficient. You can say that they are electron deficient species. They are electron deficient species. So all electron deficient species are said to be electrophiles. All electron deficient species are said to be electrophiles. Is that okay? So that is that for electrophile. Example of an electrophile is magnesium 2+, said this before, BF3. All these ones, they are electrophile. Lewis acid generally are what? Electrophiles. ETC. So all these are electrophiles. Now let us look at mesomeric effect and let's look at mesomeric effect. Now what is mesomeric effect? Mesomeric effect is an interaction between 2 pi bonds or between 1 pi bond and a lone pair of electron. Electromeric effect or mesomeric effect is an interaction between 2 pi bonds or 1 pi bond and a lone pair of electron in a molecule. It's a permanent effect. Now, for instance, let's say you have CH2, double bond, CH. This one continues like this, CH, double bond, CH2. Now, there can be an interaction here in such a way that this one will donate its electrons here. And in chemistry, whenever atoms are donating electrons, what happens? This one become more positively charged. And this one is donating its electron, here become doubly bonded. Now, the valency of carbon will not be 5 because if you count this 1 plus this hydrogen 2 plus this one 3, 4 plus the one incoming 5. This double bond cannot stay. So what will happen? This one will also have to pack on top of here to form a negative charge. So at the end of the day, you are going to form a compound like this CH2, CH, double bond, CH, then CH2. What will be on top of here? Negative charge. And here will be what? Positive. Why? This one is leaving here. You know that this electron or this bond here is formed between this CH2 and this carbon. Only the carbon is taking it to another position to bond with another atom. It will take the electrons of this carbon along with it to this position. So this carbon now is donating its electron to this other carbon here, making here to be positively charged. And then as it's coming here, this cannot stay, then this one have to pack on top here to form negative charge. This interaction between these two pi bonds, of course we know that wherever we have a double bond, one of the bond is a pi and the other one is sigma. So there's a pi bond here, there's another pi bond here. So the interaction between these two pi bonds is what is called what? Mesomeric effect. This is what is called mesomeric effect. Okay? So that is for mesomeric effect, or between a lone pair of electron and a pi bond. For instance, let's look at a lone pair of electron. Let's say this is benzene ring, okay? Now, this NH2. This NH2 is having two lone pairs of electrons here. These two lone pairs of electrons can pack here. As they pack here, what will happen? This double bond have to leave and pack here. And at the end of the day, you form something like this. You form something like this. This one will come here to form a double bond here, then NH2. Of course, you said that this one is donating electron to this place. Here will become positively charged. Then here will become what? Minus, because this one here is packing to this position, and then you have your double bond. All these effects are called mesomeric effects. Now, the next one is explain how pH of a solution affects the structure of an organic compound. Now, the pH will determine if the compound will be acidic in a mixture or it will be basic in a mixture. Now, we have to use the Anderson-Heisenberg equation to explain this. Now, the Anderson-Heisenberg equation states that pH is equal to pKa plus log A minus all over HA. Now, what is the significance of this equation? Now, whether a compound will remain as an acid or a base is dependent on the pKa of the solution and the pH of the compound. What did they worry this? Not pH, rather, and the pKa of the compound or of the solution. The pKa of the solution and the pKa of the acid, which is the compound. Are we getting it? So whether it's an acid will lose its proton in a solution depends on the pKa of the solution and the pKa of the what? Acid. Now, if the concentration or if the pKa is equal to the pH, what will happen? The concentration in the acidic form will be equal to the what? Concentration in the blood, basic form. So both the acidic form and the basic form will be present. Acidic and basic will be present in equal amount. But if the pH is less than the pKa, if the pH is less than the pKa, what does that mean? It means that the compound will exist more in the acidic form than in the basic form. Now, how about if the pH is greater than the pKa? What does that tell us? It tells us that it will stay more in the what? Basic form than what? The acidic form. Than in the acidic form. Now, from calculation, you'll be able to tell the correct answer to this using those calculations that we've done before. From there, you should be able to write something. Like when they say this one is 100 times this, it means that the pKa is less than pH, like that. You discover, how did we calculate? If you look at all the calculations we did under this, let me take one, for instance, to explain this better so that you understand better. Now, let's look at this one. Say calculate the pH of the solution if the concentration of its acidic form is 100 times is 100 times greater than that of its basic form. Now, when you calculated, when the acidic form is greater, what happened? The pH is less than what? The pKa. So the pKa was what? 6.4. And the pH was what? 4.4. So you see that when the acidic form is greater, or when the pH is less than pKa, the solution is mostly in the what? Acidic form. That is why they say the acidic form is 100 times greater than the what? Basic form. Now, look at the other one that we calculated. There was one we got 7.4. Now, that one of 7.4, it means the pH is what? Greater than pKa is what? 6.4. This is pH greater than pKa. So when the pH is greater than pKa, what did that one tell you? It tell you that the basic form is what? 10 times greater than the acidic form. Is that understood? So this equation now is what we tell you which is greater and which is not greater. So in a solution where the pH is greater than pKa, what does that mean? It's telling us that the basic form will be more, like in this case, basic form is 10 times acidic form. So it will be greater than the what? Acidic form. Okay? Why, if the pH is less than pKa, as in this case, the pH is what? The pH is calculated to be 4.4. Why the pKa is what? 6.4. What does that tell us? It tells us that the acidic form is 100 times greater than the what? Basic form. So that is the essence of all these calculations we did in this. And I believe we've come to the end of Miss Ebire's part of the course. And I believe that there is nothing that she wants to set again apart from these details that she has already given to us. So thank you for your time. Please make sure you subscribe and turn on the notification button so that you'll be notified whenever we post a new video. Thank you.